Okay, so let's start off AP Physics by going over kinematics. So kinematics, I would say, is it's almost purely a mathematical foundation. So it's really like just learning about coordinate systems and really rates of change. So the first thing I would like to talk about is position. So position. Position is simply where the object of interest is at a given time or as a function of time. Okay. So if I start at, I'll maybe show with a drawing real quick. Let's try this. Okay. If I start, let's say we're running on the beach, I don't know, could be anywhere, and I start here. We're going to call this the origin, and we're going to call that X initial, the initial spot I start at. And let's say I take off running for some amount of time, and I go down the beach, and I end up here. Right? Well, this is how far I am after some amount of time. So we'll call this X at some time. So you'll see X, we'll call this X naught. That's what the circle is. This is the initial position, and this is our position after some amount of time has passed. And we could plot this, right? I have moved forward. If we consider this direction positive, then I have gone forward some positive amount in terms of my origin. So we could plot this over time. I could say, and I'm not going to put X on the, like I'm not going to call this X because this is going to mess with you guys right now, but let's just call this position. And the X-axis in physics is almost always time. Now, there's some kooky professors that will put it on the Y-axis. I had one of them in college, but for the most part, we put time on the X-axis. So let's say that, I ran at a constant rate forward. My position versus time might look something like this. Right? So I'm constantly increasing my position with respect to time. If I ran at some non-constant rate, like let's say I was slowing down over time, right? Like I'm running, but I got tired and I'm slowing down, my position might look like this over time, right? I got slower and slower. I started out good. And this is, again, time. And this is position. All right. The rate of change of position with respect to time, the slope of this graph has a special name. It's called velocity. And before I move forward, I need to say that position is a vector. So these guys get little vector hats. Okay, the arrow means that, hey, this thing has a direction to it, not just an amount. But, okay, the slope of this graph, the rate of change of the position versus time graph is called velocity. So if I were to take this slope, rise over run, if we were to do x2 minus x1 over t2 minus t1, a more convenient way of saying that is change in x over change in time. The triangle means change. We get something called, this is all equal to something called velocity. Right? And we'll typically denote velocity as some function of time as well. So we can say velocity to p if we want. And that is the slope of the position time graph. Now, if I'm talking about a constant increase in position with respect to time, the velocity wouldn't be changing, right? The slope of this graph would just be some number, and it's constantly that number over time, right? So if I calculated the slope of this thing, assuming this is straight, I've done my best job to draw it straight, right? And I calculate the change of x over the change in t, we'll get the velocity. And we might do that as an exercise in class where you actually calculate the velocity, right? Let's say I went, 3 meters in 2 seconds, then my velocity would be 3 divided by 2 meters per second. So we could say that x, I'll go ahead and do it. We'll just do it as an example. But the x initial oftentimes is 0. We consider the starting position to be 0. So we would say 3 is how far I ran, 3 meters, minus my starting position, which was 0, right? Let's say, I ran 3 meters, not that far. But this is 0 meters, right? And I ran 3. 3 meters minus 0 meters, and let's say it took me 2 seconds, over 2 seconds minus 0 seconds gives you the velocity in terms of meters per second. And we say that's 3 over 2 meters per second. And in physics, we typically use decimals, so we call that 1.5 meters per second. Okay? All right. This is a constant value according to this graph. I ran at 1.5 meters per second the entire time. Here, that value is changing. The slope at this point here is different than the slope at this point, right? This is a non-constant velocity. And that leads us to something called acceleration. So the change in velocity over the change in time is called acceleration. You'll notice that this thing has a non-zero acceleration over here. The velocity did change over time. Here it didn't. This would have an acceleration of 0. I'm going at a constant velocity. So let's define acceleration. Did I ever type out velocity's definition? I just did it mathematically. But first, okay, let's go ahead and put velocity definition. Velocity is change in position over change in time. Acceleration is change in velocity over change in time. So let's take a look at the position time graph in terms of the velocity first, and then we'll look at the acceleration. So if I were to graph the velocity against time for this first position time graph, right? The velocity as a function of time is constant because look, it's the same, right? The position's increasing at a constant rate. Therefore, this velocity, we calculated it arbitrarily and said it was 1.5 meters per second. It's that the whole time. So if I were to say the velocity as a function of time, well, it's just going to be this 1.5 value, this 1.5, the entire time, right? That's what our graph would look like. Now, this graph would look different. Let's assume here that I'm constantly slowing down, right? I'm getting a little slower all the time. Now, this graph isn't the best drawing of that, but if we assume that I was constantly slowing down, get that eraser out real quick. If we assume that I'm constantly slowing down, the velocity would be decreasing, right? That's what it means to slow down. So the velocity would be decreasing at a constant rate against time. And eventually I'd stop. And maybe I'd start running backwards. Probably not. But that's what our velocity versus time would look like. Right? Now, this is a fundamental part of physics. Being able to go from position versus time to velocity versus time to acceleration versus time, right? So here you'll notice there is no acceleration, right? The position increases constantly as a function of time. That means the velocity is a constant number, which means that there's no acceleration. If we were to try to plot acceleration for this, I mean, I shouldn't say there's no acceleration. It's that the acceleration has a value of 0, right? The object is not accelerating. It's staying at a constant velocity because, as we said, the change in velocity over the change in time is acceleration. And here, there is no change in velocity over change in time. If I do v2 minus v1, I get 0, right? Time is progressing, but the v value is not changing. So acceleration versus time graph would be a constant line. Oh, I'm glad that this thing tells me. I had to switch to a different screen recording thing. But this would be a constant line along 0. And I'll save the next case for the next video so I don't want to run out of time. But think about what this graph would look like for the acceleration versus time. All right, I'll see you in the next one.